Without a doubt, the biggest challenge that we had was to resolve the issues related to the injection system. What I mean by that is the dimensions of the machine require a lot of power during the injection phase. And filling a die that is so long yet with such small wall thicknesses is a challenge that needs to be faced. We already had some ideas about the next evolution of the injection based around the hydraulic regenerative solution. However, the volume of oil for which we now must control was very challenging. We had to move a lot of aluminium very quickly, and in terms of hydraulics, this is always a problem. When you move fast, normally you sacrifice power or force. We had to come up with a new concept, and we were able to do this by focusing the team on the dynamic force of the injection. Here in IDRA, usually we like to say that nothing is impossible, but for sure it was a very daunting to push the machine systems to have a cycle time that was shorter than the existing machines. For many years, the 4,000 ton was the biggest in the market, and we had established a stable minimum cycle time that the machine could produce parts. The die casting process is a thermal process, and as such, whether it's a 4,000 ton or an 8,000 ton, the thermal dynamics of the tool remain similar, meaning that we have to maintain the correct temperature in the tool and have a cycle time that is more or less the same as the 4,000 ton. At the end, we were capable to do this better than we thought possible, and the 6,000 ton will actually dry cycle faster than the 4,000 ton. Given that this is a machine that weighs over 400 tons, this is an incredible feat and something that me and the team are very proud of. Whenever you try to do something new, there are always a lot of skeptics, and certainly at the beginning of the decision-making process, there are a lot of questions about the validity of having such a big machine, when the customer requests in reality didn't exist. Several sub-projects had to coincide to make the machine work, and it was indeed a team effort within IDRA, involving many different departments. The most important part is enthusiasm and a strong belief in what you are doing, and our head of design was convinced that the 3-platen concept for the press was not yet exhausted. As such, he was inspired to push the boundaries of mechanical engineering. When we first started thinking about this, our target was the Tier 1 foundries. These are direct suppliers to the automotive producers, who generally tend to be larger businesses with global manufacturing facilities. Due to the size of the castings and the requirements from facilities logistically, it is important to be located close to the vehicle production line. The machine is 20 meters long and nearly 7 meters tall, so there are no existing buildings available, and all of the interesting companies are forced to think about new construction. Our objective was to create a new field of light alloy production, helping the producers achieve the difficult CO2 targets set by the governments around the world. Change was needed, and the light alloy foundry community was worried that the advent of electric vehicles could kill our sector. ICE, or internal combustion engines, have for many years been the sable product targets for our customers. Gearboxes, sumps and engine blocks are produced using secondary or recycled aluminium. There is a real danger that in the future these will not be needed anymore, as some governments continue to push forwards to abandon the use of ICE vehicles. The GigaPress offers a real alternative for the international foundry community, and together with the Neo-class medium-sized machines, we can continue to be the industry of choice for the automotive designers and vehicle lightning.